Hello everybody, welcome to our session Bias and Fairness 2. My name is Elisabeth Lex. I'm from Graz University of Technology in Austria, and I would like to welcome our first speaker who will be talking about bias user history synthesis for personalized long-tail recommendation. The paper will be presented by Elan Markowitz, and I would ask our speaker to the stage. Thank you.
All right, hello, good afternoon, RecSys. So I'm very excited to be talking about this today. This work is biased user history synthesis for personalized long-tail item recommendation. This is work done by colleagues of mine at USC and as well as Riverside. Actually, the Information Sciences Institute is a neighbor of the Institute for Creative Technologies that Mark spoke about this morning. But yeah, so I'm not the corresponding author, but I am excited to be presenting. So the issue we're addressing is called the long tail problem, and we heard about this in the earlier session because, well, for the same reasons, is that the long tail items, the items that aren't as popular, are really hard to give good recommendations for. So, you know, this is one example where we have, this is roughly 20% we classify as head items in this picture distribution. And those are the items that are very popular. A lot of people see them, most people. And, you know, so when we're training our recommendation system to predict what a user might want to see, naturally that bias gets amplified and the recommendation system promotes those head items. So we have a trouble, which is one, we don't recommend tail items, and then two is that we don't train as much on the tail items and have as much data, so our representations are worse. So we could just push more tail items at the user, but ideally we want those items, those tail items we promote to actually be good recommendations. So the basic model, you know, for recommendations deep learning, the two-tower neural network, we have a neural network that encodes a representation of the user and a neural network that encodes a representation of the item. Now, this is very common. And here we can encode categorical features, dense features, etc. And then finally, we'll interact them to get the relevance score. So we use this as a starting place, though it's not the only architecture we evaluate on. But the way biased user history synthesis works is we take the user tower and we add in a synthesis step. So in this step, we start by sampling from the items that a user has interacted with. This is very common. And the key step is that we sample not based on a uniform distribution or most recent, but a distribution based on the item degree. So in this case, the softmax of the inverse degree. And there's some theoretical motivation for this as well, which I won't do all the theory, but the basic idea is that, you know, if someone told me they've watched Harry Potter, you know, a lot of people have watched Harry Potter. So it doesn't give me as much information, but if I know someone's watched a documentary on the history of shoemaking, not a lot of people have done that, probably, I assume. And as a result, that's a more informative piece of information. So motivated by that, we sample this bias distribution from the user history. We then do an interaction where we, you know, create a better user representation based on their biased user history. So that's the synthesis step, and we have three different modules we experiment with. One is just a very simple mean aggregation of those interacted representations. And I should have mentioned that those item representations are the same as from the item encoding tower. So we take the item representation and we aggregate them into the user embedding as either a mean with an attention layer or a GRU, so a gated recurring unit. And so we experiment on movie lens and book crossing. In this presentation, I'm mostly going to focus on the movie lens data. Both have about 1 million interactions. The movie lens is a smaller distribution. There's fewer items and users, but the results hold up with book crossing as well. So our results are here, and we separate the results into the overall performance, the head item performance, and the tail item performance. The metrics are, hit rate and NDCG. I'm not going to go into the details. I assume, the majority of you, if not everyone, is familiar. At the top is our base model. That's the two-tower neural network. Our baselines are a combination of model-agnostic learning frameworks for promoting tail items or just improving representations, and as well as some architectural model changes. The results at the bottom are the bias user history synthesis results, where we have the mean, attention, and GRU variance of that. Now, what we can see is that it's not as easy to get improvements on the tail items. In fact, even some methods that state that they can, depending on the data set, may or may not. And what we find is that the bias user history synthesis can greatly increase performance, but not just on tail items, on head items as well as tail items. And part of the reason is that good work went into the implementation and experiment, as well as also that those tail items are more informative. And then in addition, the sampling, the stochasticity of it, acts kind of like a dropout in enabling better generalization. Now we see that the bias user history synthesis with the attention module does better on the tail items, at least in movie lens, and the GRU is the best overall. So we'd encourage you to experiment on what works best on your data. And also worth noting that even the very simple mean aggregation can improve tail embeddings quite significantly, tail predictions, with a 17.5% improvement on the hit rate. This is a random sampling of 6 users and the items they've interacted with. The red is the head items, blue are the tail items. We see that in the base model, there's not very much separation between head and user items, if any at all. And in the user history synthesis ones, we see a very clear separation between the representations learned for the tail items and the representations for the head items. On top of that, we see that there's more variance, and so even within those tail items, we have more variance in the representations learned, meaning we're better able to parse out which of those item representations, which of those tail items you might actually want to interact with. We also note that the model is, this approach is somewhat agnostic as long as you have an item and user representation, you can apply bias user history synthesis. So here we experiment with the two-tower neural network, but also wide and deep FM. So both are kind of common models, and we see that the base model in gray doesn't perform as well, and across the board, bias user history synthesis improves the results here. So specifically, we see that maybe the GRU is actually the best overall, but it is a bit data set dependent. And yeah, mean, even though mean is very simple, we still see very good improvement, especially on the overall. There's a little more discrepancy in the tail distribution. So we also want to note that the sampling stochasticity helps with training times, and we see that this is the per epoch training times, and we note that they're not any different than comparable other methods, other learning methods. And specifically, we can see, the mean aggregation, so that the whole difference, the sampling approach, comes with almost no cost to the training time. So this is a very practical model, architecture, and application. And even for the GRU and the more complicated models, we see that it's still comparable to others and on kind of the same order of complexity. So kind of in conclusion here, the biased user history synthesis, we're addressing the long tail problem, improving not just the amount of tail items recommended, but improving the quality of those recommendations as well. We see that the quality improvement doesn't hurt head item performance. In fact, it still improves it. So there's no trade-off there. And it's applicable to multiple base architectures and efficient to run. Now, the paper itself has further details on the softmax temperature, how many samples, many other details. So give it a read if that's of interest. And then, yeah, finally, check out our code. It was designed to be used. So code and links are in the QR code. Thank you, and I guess if there's any questions.
Thank you, Elan. So we have a question in the chat. I read it to you. How do you propose tackling user item features such as the number of times items from category X were liked by users from country Y? It is hard to synthesize as a user-only feature in the synthesis module.
So that was on categorical variables, or I missed part of that question.
Yeah, sorry. I'm just reading it. So basically, is it hard to synthesize features that are derived only from the user for the module that you have?
Yeah, so the approach starts with the same features you would use in the item encoding. So the item, I could go back, I'm not going to go back to it, but we had the categorical features and dense features. The categorical features are, we get embeddings for those, and for the dense features, we apply a linear layer just to get like a initial embedding and concatenate all of those and combine them. So any way you get your item representation, you can use in the synthesis section.
Mm-hmm. And I think we have time for a brief second question, also from the Slido. Why did you modify the user tower, not the item tower? Given that we're trying to distinguish and learn better representation of long-tail items, what's the effect of modifying the item tower instead?
Yeah, that's a good question. So I guess conceptually speaking here, the theory is the items are informative, especially the tail items, are informative about the user preference. You could maybe make a similar argument for the user case, and maybe that could be a future work. I guess conceptually, in that case, you're saying the users who interact less with the system are informant of the, of the item. But I'm not as confident that kind of premise holds.
Thank you. Thank you. And please approach Elan if you have more questions or ask them in the Slido. Let's thank the speaker again. And our next presentation